Our last topic with retaining walls are brace cuts. Up until now, all the walls, anchored walls we've looked at, have had a single wall with no more than one anchor. There are situations where we need two facing walls or we need one anchor or both, and brace cuts generally fit both requirements. Brace cuts are sets of walls, in other words, two walls in parallel, which are used to create a mechanical ditch. We're going to consider a sheet pile version of this, inside of which construction can take place in the dry. It used to be more common than it is now, but you still see brace cuts being used. Probably the best known type of brace cut are trench boxes, which are designed in an entirely different way because they're not anywhere near as deep as what you're looking at here. We looked at brace cuts in soil mechanics as part of in terms of the permeability issue. In other words, if you had one under the water, you would need to keep it dry and keep it from having soil boiling issues. In this case, we're going to flip it over. You've got other issues, including the bearing capacity issue, where basically the cut acts as a reverse shallow foundation. We're not going to spend a lot of time on that particular subject. Brace cuts is a fairly complex topic, and there are many different ways of analyzing them. Just the same brace cut. In other words, no different things you need to look for. We're going to concentrate on the design of the supports, the braces, and we're going to also concentrate on the design of the sheeting. Tied back walls. If you have a tied back wall and you've got a situation like this, the braces outside of the braces in the soil. The braces here are in the cut, and I think some of you may recall from soil mechanics about that. The original work for this was done by Carl Tersaghi and Ralph Peck back in the 1940s. What they discovered was that the progressive excavation placement of braces altered the lateral earth pressure profile. There's a little more specific, and it gets into, again, this is a fairly complicated topic that Tersaghi and Peck attempted to reduce to an analytically simple one. And they partially succeeded. Basically, the thing that is not, and there's a lot, and it's typical with any other design method, much of this has been lost to much of the import of what they were doing. A lot of the details have been kind of lost in the narrative's been lost. But basically, there were two things that were going on. First of all, brace cuts are built progressively. You may recall from my discussion of SBW 2006 that SBW 2006 has loading cases where where normally what we use the software, we had one loading, we had the loading case 0, the same on both sides, then we excavated, quote unquote, the dredge side, and we had no soil there, and then you have your unbalanced forces and your tie back or not tie back, perhaps. And you can take that, and then you can analyze your wall. You can also, you can also do it in stages. In other words, you can take a brace cut. You can take a sheet pile in case 0, where you've got soil on both sides. You can do one where you come down a little bit, put a brace in there or anchor. It reverses the sign of the DW, but it's still. And then you can analyze that. And then you can excavate some more and analyze low cut step 2 and then low step 3 and 4, and how many low steps you want to do it. Some sheet pile walls require this type of analysis. Brace cuts did, but their work was largely interacting hand solutions with experience. with what they were seeing. That's one thing that's important to remember about brace cuts. The other thing, and this is all really important, is that their primary objective, design objective, was not to determine the whether, keep the internal stability of the wall. In other words, their one of their main discoveries in this was that their primary concern was not that the wall would bend and break itself, but the moment failure. Their discovery was the biggest problem was the bracing collapsed in many circumstances, and bracing collapsing is a catastrophic type of failure, and as a result, the emphasis of their technique is on the design of the bracing as opposed to the design of the sheeting. If you stick with the bracing, this method is fairly simple. Their results are fairly simple. Unfortunately, what's happened is that in order to we're still left with, well, this is terrific, so what's our sheeting? Well, that's where things start to get complicated, and that's where things start to get a little complicated, and that's one of the reasons why solving these problems can be difficult. So basically, in order to fix that problem, they applied some computationally simplifying assumptions in order to get to the bracing was easy to estimate the loads according to their technique. And I'll discuss that in a minute. The complicated part was transferring that over to actually calculating the moments on the sheeting, and by that the bending stresses of the sheeting. Okay, the sheeting brace cuts have a pressure distribution system, and it's entirely if you get a brace cut, you have a pressure distribution which is different from that of the standard active and passive and whatnot. There are three basic cases. The first is sand. The sand is pretty simple. They actually discovered that if you have the wall height down to the bottom of the excavation, that the pressure along the sheeting is equal to 0.65 times the Rankine pressure of the soil, or the Rankine active earth pressure coefficient, times the unit weight of the soil times the height. And therefore you can, that's pretty simple. It's a fairly uniform. And the way that they did it was the following. Let's say here we have 4 different supports, F1, F2, F3, F4. The way they did it was the following. They would take halfway between the difference between F1 and F2, and they would assign the pressure above that halfway point to F1 and then the bottom to F2. They would do the same thing, and they would split the beam in the middle. They would assign this pressure to F2 and this to F3, split it again, F3 to F4, and then they would have a soil resistance at the bottom that they would split F4 and this soil resistance at the bottom to. And that's how they came up with the bracing loads. That's pretty simple. It's very reminiscent of what we did with MSE walls, where we basically bisected the distance between one layer of geogrid or whatever and the next layer. We basically took the half out of the middle. If you had a nice uniform distribution, that made the math a little simpler. With brace cuts, you frequently don't have it. MSE walls, it would be more common to have a uniform. With brace cuts, no, you don't have that. Soft to medium clay starts out at 0 at the top, and about a quarter of the way down the wall it comes to a max, and then it goes straight down. For stiff clay, you have a sort of a trapezoidal distribution. It starts here, goes up to 0.25. 3/4 of the way down, it comes back to 0. And the maximum value in both cases is determined by this Ka, which is computed here, times the gamma times the height. And that is true in the case of the soft or the medium clay. The gamma, the stiff clay tends to bracket the two, and these rules that we have here on the slides show you how to deal with ambiguous situations. But most importantly, they show you the difference between a soft and medium clay and a stiff clay. They show is based upon the stability number, and the stability number is given right here. For clays, base the selection between this and this on this stability. So if you follow if you follow the directions, you can pretty much figure out which way you're going on this. Those distributions are different from what we've dealt with retaining walls, period, up to now. Now, applying these to the brace cuts is a little complicated in the clays, because and you can see here it illustrated, the location of the struts, or the braces, excuse me, the location of the braces and the location of the break points aren't the same. As a result of this, there are a couple of ways, and if it's just for the bracing load, it's not a problem. You can divide up and pretty much kind of, what you would do is you could divide up, and then you could you can once you divide it up, you can then you can actually take this triangle load, put into a resultant, and then you can take this load here in this section, put that in a resultant, and then you've got a nice uniform there, put that in a resultant, and then you can basically break down your distributed loads into concentrated loads. That will result in a higher moment in the sheeting, but under these conditions it's permissible because you will get the exact same loading on the braces. In order, the tricky part is this. In order to, because of the way in which the brace loads were developed, basically for any for any support point other than at the ends, and sometimes the ends are at the ends and sometimes they aren't. For example, down here you'll notice there's a gap, and then that does the cantilever. You'll see the same thing in the top very frequently, where it'll stick up above the top. That too is a cantilever. And so these so therefore, if you do that, other than that, all of these are not only simply supported, but each of these sections, this segment right here, and this segment right here, and this segment here, are analyzed, and this one right here and this one right here are analyzed as simply supported beams independent of anything to the right or the left of them for the purposes of computing moment. My suggestion, now I have a tutorial on how to do this, and it's a little complicated, and it involves the use of finite element software. You can use beam software and get pretty much, with this distribution, it's not really a big deal one way or the other what you do. I mean, it's uniform. If you got the sand, it's uniform, nice uniform distribution all the way up and down. It pretty much takes care of itself. Uniform, you can actually use your steel book. Now, I was criticized one year in class because I said, you can find this in your steel book. And I was criticized because they could not find it in the steel book. For those of you who have trouble, this is what I'm referring to, and I'll put this up to the front to make sure you can see what I'm talking. This is a very old steel book. And so those are the formulas I'm talking about. And of course, AISC cleverly moves these around to keep everybody confused. One of the reasons why I use the older steel books is I have a hard time finding anything in the new steel book. So sometimes you have to because of section changes and whatnot. But a lot of the older engineering still applies. Of course, it also depends on the code environment you're in as well. What I do for structural design is free from code requirements, but has some peculiarities of its own. Let's put it that way. So that's that. You know, you could if for this you can, and you're always allowed to take distributed loads and make them concentrated loads. That's always permissible with this. You will get higher bending moments than normal, but it's not, you know, for this type of application, it's not a big deal. The big, you know, it beats having the sheeting buckle. Let's just put it that way. And I go into, but again, I have a tutorial on there. I may add a video, some video aids to that. I'm working on that to get you know, to give you a little bit better idea of what I'm doing. Beam software is very useful in this situation and can be applied from one segment to the next and would be, in my opinion, the best way to design this particular, to do this in a contemporary environment without having to resort to just, you know, straight up, you know, without getting anything terribly fancy. This is sort of a summary of design criteria for brace cuts. Some of these are applicable to your. Some of them go more into the bottom heave issue. I would like to have time, but I don't really, to deal with the bottom heave issue in brace cuts. It's the reverse kind of. It combines two things. One of them, of course, is, you know, the soil bowling issue we talked about in soil mechanics, and the other one is it's a bearing capacity issue in reverse. And that's really what most of this is about, the brace, you know, base stability for brace cuts in the bottom. This is a design example by hand. It incorporates what I'm talking about. Like I said, I don't, for this particular problem, I don't recommend the use of pure hand calculations. If you know, but the setting it up in Beam software or FEA is simple if you can get the end conditions. It is tempting to model this as a continuous, simply supported beam, but that's not the way that Terzaghi and Peck intended it to be done, as far as the way it, you know, that may result in, and I think that would be an interesting study, may result in the redistribution of the earth pressures along the beam. So again, I have a fairly detailed explanation of how to do that, and I would suggest you look at it. And like I said, I may do a video on that as well. Tied back walls have similar issues, and but the distributions are different. In fact, the distributions are very similar to those of sand, but they're both uniform. So if you get a tied back wall, then the situation is much simpler than it is with a brace cut. And again, tied back walls assume that they're, you know, they again, with the excavation issue, you excavate some and you put a tie back, and you excavate it some more and you tie it back again, that sort of thing. So that concludes this presentation and series of presentations on retaining walls. We will get in the deep foundations next time. Until then, thanks for watching, and God bless.